I'm back. So now let's talk about the second part of this chapter. Um, we were going to start to talk about resting membrane potential, difference between action and graded potential. What is a synapse? That's what we're talking about here, okay? So membrane potential. Let's remember that every cell has a resting membrane potential. And then the cell can go from resting to action, and that happens only in neuron and muscle cells. Okay, the other cells don't have this active phase of a potential. They just act like a battery, so their membrane is polarized because of what we're going to remind you of now. That is part of a resting membrane potential, but they don't trigger, they don't have this ability, this excitability in the membrane to trigger an action potential like the neurons and muscles. Okay, so the other cells don't. So you have definitions that we need to know. Voltage is a measure of potential energy generated by separated charges. You're going to have three types of channels that we're mostly going to talk about the first two. Chemically gated channels depend on a ligand. In our case here for neurons, it's going to be a neurotransmitter that binds to a channel and opens a gate. So sodium goes in the cell, okay? Voltage gated are channels that can open because the membrane is getting depolarized. So when that depolarization reaches that voltage gated channel, that opens a gate, more sodium goes in. Okay, and then the same thing is going to happen to potassium during the relaxation or the hyperpolarization period. So how these gates happen, operate, like just told you, right? One depends on a receptor. I found my pen. So the receptor will bind here, and then sodium, when that gate opens, sodium is going to be able to go in, and potassium is going to be able to go out. Okay, same thing for voltage gated ion channels. The difference is that here, what makes the channel open is not a neurotransmitter. It's the fact that the membrane is depolarized. You see how it was positive outside and negative inside when it was closed? To open, it depolarizes the membrane. It gets negative outside and positive inside. How does that happen? Because sodium is going in. When sodium is going in, what's going on? Remember, there is a lot more sodium. Let me show you this in the next slide. Hold on. So we have, and we can measure this potential but with a voltmeter. Okay, so this is how you know what is the voltage. I'm not going to ask you how much is the voltage in a membrane, but you know there is always a difference between how positive and how negative the membrane is comparing outside and inside. Okay, so resting membrane potential. What's going on here? You have type of channel that is able to send sodium out and potassium in. What is this? This is the sodium potassium pump. When does this happen? This happens because before this, what you had was sodium going in. Why? Passively. There is a lot more sodium. So the top here is the out of the cell, right? Here is the inside of the cell. There is a lot more sodium out, always. A lot more, okay? So sodium goes from where it's more concentrated to where it's less concentrated, right? Potassium, the other way. There is a lot more potassium in the cell than out of the cell. So potassium has a tendency to leak out through these chemically or voltage gated channels that are, in this case, is more, they don't need a stimulus. They're leaking channels, okay? So they leak sodium in, potassium out. What is the sodium potassium pump going to do? This is going to generate this charge in the membrane. Positive outside, negative inside, right? When this is happening, this means you are able to keep a membrane potential. Let me just see if I'm telling you the right thing. You're able to keep a membrane potential because you are doing a maintenance of this leaking of potassium out and sodium in by using the sodium potassium pump that spits sodium out and spits potassium in. So it does the opposite of the leaky channels. Why do you need that? Just so not all the sodium gets in the cell and all the potassium out. It's just a maintenance, right? Some sodium goes in, potassium goes out, and then the pump reverts it. Make sense? Okay. So this is the resting membrane potential. What happens during, so this is again the same thing I just told you, okay? Leaky potassium channel, leaking sodium channels, sodium going in, and then the sodium potassium pump helping everything to go back to equilibrium. So this generates that positive charge outside and that negative charge inside. So this is here, right, is this part of the graph. So now we're going to talk about how depolarization happens. And that happens because you have the opposite thing happening. So what do you have in this case? So we have the same players. We don't need to talk about them again. Let's talk about the action potential. So we have first, sodium in the resting state is going in, right? And coming out through the sodium potassium pump and all that's going on. During the depolarization, you have more sodium going in because this is also a leaky channel. So the same thing that happens during the regular resting potential and potassium leaking out. But because this is only the passive process and it doesn't happen, it happens more quickly than the resting potential. Then and there's no sodium potassium pump to kind of like correct it. So you have an inversion of the charges because you have a lot more sodium going in than potassium going out. So the membrane becomes more positive inside than outside. That's depolarization, okay? When that happens, you get to a point that there is no more stimulus for this channel to be open because the voltage is slowly going back to normal when it reaches the peak of the graph. These gates close, okay? And then the only thing that keeps open is the potassium gate. So a lot of potassium leaks out, making the membrane again positive in the outside and negative in the inside. This is the repolarization part, which is this part here. Okay? And then the hyperpolarization is the fact that when in the end of this process, more potassium than you really need leaks out, and the membrane becomes more positive in the outside than the resting potential. So you have like a decrease in the voltage for a short period of time, and then it goes back to the resting potential, which is here, which is back to here, right? So you see how this is lower than this. So this is hyperpolarization. This is just regular polarization, and this is depolarization and repolarization, right? So this cycle keeps happening as you are generating or propagating through that plasma membrane an action potential, okay? When we talk about graded potential, this happens, but it's localized. So this is what happens in a graded potential. You see how there is a depolarization in this part of the membrane? Okay, this propagates just, you see how it started here, and then it keeps moving to the sides. But it's localized. It's not going to go anywhere other than this part of the plasma membrane. So this is an axon, right? So this is one plasma membrane, that's the other side of the plasma membrane from the axon. So the depolarization doesn't spread much further when you have a greater potential, because these are slow potentials, okay?